Hello, welcome to this video. This is for Lesanani, and this is from summer 2020. This is paper 42. And cadmium ions form complexes with methylamine and with 1,2-diaminomethane, as shown in equilibrium 2 and 3. And there they are. An equilibrium set up between these two complexes is shown, and there's equilibrium number 4. Ec4 is the equilibrium constant for equilibrium 4. Write an expression for ec4, kec4 in terms of k stab 2 and k stab 3. Okay, so basically we've got to figure this out, get this one from these two. All right, how are we going to do that? All right, so let's write down equilibrium 4. Well, it's a lot of writing, but never mind. We've got cadmium. Let me pause the video and come back when I've written it all, because otherwise it will take forever, won't it? Okay, let me try that. Well, there you go. I've written everything out. It's a lot of writing for 1 mark, I must admit. But here we have K step 2 on the left. This one's K step 2. And this one is K step 3. Now, don't forget, in K steps, you don't include water. Okay, these aren't included, the water terms. All right, but this is an equilibrium constant. They want an equilibrium constant for equilibrium 4. And I've written out what we're after. We're after this. How do I get this from these two? Okay. Now, Lesanani asked an interesting question. She says, why don't we negative it? It's only negative when it's a vector value. Equilibria are vector values. And therefore, reversing it will reverse the sign, because the energy direction is in a different way, isn't it? If it's exothermic one way, it must be endothermic the other way. And we show that by changing the sign. But these are simply ratios of concentrations. So these aren't actually valent. What's the word? These aren't actually vector quantities. These are scalar, and they're just purely ratios. So, for example, if the equilibrium constant one way is 2, the back way will often be 1/2 or root 1/2, depending on the situation. All right, but you don't change the sign because they're not vector quantities. So anyway, we've got to get this from these two. All right. Now, as you can see, what's on top? This is on top. This CDEN2, and that's that one. So I'm going to say K stab 3 goes on the top, because we need those things on the top. This is on the bottom as well, the EN squared there, and this is on the top, which is there. In this one, this is on the top here, but it's on the bottom here. So if I divide this by K stab 2, then, as you know, this flips around, doesn't it? So this goes on the top. And then I guess you can cancel things out, but it looks to me as it will be K stab 3 over K stab 2, and it will give you this. All right. I hope that makes sense. There's a lot of writing here for not many marks. Anyway, let me get on with the next one that she's asked about. Let me pause the video while I clean this up a bit. Okay, here's the next one. Lesanani wants to know about magnesium iodate decomposes when heated to form that, and that. And if you look at the mark scheme, what they've done is they've been a bit cheeky, and they've just put a 2.5 here, and that's balanced now. Now, I must admit, said you've got to include whole numbers, and I'll stick to that. They prefer whole numbers, okay, when you're balancing. Now, they didn't here, did they? And this is for sure, this is what's on the mark scheme. But you know what? They're a picky bunch, Cambridge. Sometimes they want whole numbers, sometimes they don't. So I honestly think we should times this out by 2. So we get 2 of those, 2 of those, 5 of those, and 2 of those. I'd always use whole numbers if I can. When are you allowed to use fractions? Well, fractions are allowed when you're doing delta of formation, okay, because that forces you then to form only 1 mole of a compound, and therefore you might need a fraction there. So, for example, water. If I'm forming water is formed from oxygen and hydrogen. This has to be a 1. I have to form 1 mole of water, so I have to put a half there. That's the only way I can do it. And I think it's totally acceptable to use fractions here. In fact, it's vital that you must use fractions here. But in this case, I wouldn't do it. I wouldn't use fractions, even though the answer scheme has a fraction. Cambridge are fickle. If you don't use fractions, you're definitely right. If you do use fractions, you might be wrong. So I would definitely use whole numbers. Next one is write an expression for the solubility product. There we are. This is how calcium iodate decomposes, or whatever dissolves in water. Calcium and 2 iodate, so there you go, you get this. Calcium times the iodate squared, and therefore the units are going to be that, aren't they? They're going to be concentration cubed. Okay, and what's the numerical value of Ksp at 298K? Well, I think lesson 90 wanted to know this one as well. And this one could be tricky as well. So let's get a nice blue, different color here. So honestly, I would always do this, always write out this, even though I've already written it above. But if you write this out, things become clear. Okay, so what we have here is what we got. The concentration is 5.6 times 10 to the minus 3. So I'm going to write 5.6 here times 10 to the minus 3. Sorry, no, I'm not. Let me get rid of that. I'm going to write the concentration where saturated solution is 5.6. So yeah, you dissolve 5.6. So let me start that again. 5.6 times 10 to the minus 3 here. And this is 5.6 times 10 to the minus 3. But this is 2 times 5.6 times 10 to the minus 3. Okay, so now let's work out our Ksp. It's this, which is 5.6 times 10 to the minus 3 times not this, but this squared. Okay, and a lot of people get confused about this. So, and what is it then? So we get, let's square it, it's 4, squaring the 2, times 5.6 times 10 to the minus 3. Okay, I'm going to use my calculator. Oh, there we go, nearly forgot there. So that's where the 4 comes from, little Nanny. It's 2 squared. So 5.6 exponential minus 3. I'm going to cube that, times the answer by 4. And I get 7. Where do I go here? Have I done it right? Yeah, I think I've got the right answer. I get 7.02 times 10 to the minus 7. Okay, I'm looking at the answers and that looks right. Okay, so this is one of those ones that if you have calcium, let's do this one, calcium iodate. Okay, gives calcium and 2 iodate ions. This is X and this is 2X. So therefore the Ksp is going to be X times 2X squared, not X times 2X squared. Okay, so it's 2X squared, 2X everything squared, as opposed to 2X squared. And that's where the 4 comes from that you asked about. Okay, hope that makes sense. Let me go to your next one now. Let me pause the video and clean up a bit. Okay, so this is the next one that we're looking at. Iodized salt is sodium chloride mixed with a small amount of sodium iodate, that one. And there we go. 50 grams of the iodized salt is dissolved in distilled water and made up to 250 in the volumetric flask. So the first thing I like to do, I don't know, maybe you think this is a bit childish, but I like to think of this. There's the volumetric flask, that's a horrible one, 250 cm cubed. And then we take 50 of this. So we take 50 of this, 50 centimeters cubed of this, and we put this into presumably a what are these called, conical flask, and we titrate it against my aqueous thiosulfate, and we need 12.4 cm cubed of this. All right, and there are the equations, and we've got to go backwards and find out how much of the sodium iodate is in there. All right, so there's a bit of messing around, but let's go for it. Okay, so the first thing I'm going to do is change pen. Let me get it nice and blue. So let me start off with this. Number of moles of the thiosulfate is equal to 12.4 times 10 to the minus 3 times 0.0200. This comes from N equals CV, obviously. Now I'm going to use a calculator to figure this out. 12.4 exponential minus 3 times 0.002 is equal to 2.48 times 10 to the minus 5. And I'm going to put that where it belongs here. 2.48 times 10 to the minus 5. So therefore, that number divided by 2 is going to give me the number of moles of iodine. So that's going to be 1.24 times 10 to the minus 5. This one goes up here. 1.24 times 10 to the minus 5. Now I'm going to divide that number by 3 to get the number of moles of iodine. Divided by 3 is equal to that. And that gives me 4.133 times 10 to the minus 6. Okay, so that's how much is in 50 cc's of our 250. So I'm going to times this number by 5. So times that by 5, and that gives me number of moles of the iodate is equal to 2.066666 times 10 to the minus 5 moles. Okay, now obviously that's going to equal the number of moles of sodium iodate, isn't it? Now it wants the mass, so I have to times this number by the relative molecular mass. Now the mass is, I'm guessing here, 23 plus 127 plus 48. I'm guessing it's 198, so 0.6. That's the number of moles, times it by the relative molecular mass, including the sodium, don't forget. So we times that number. Oops, messed it up. 2.067 exponential minus 5 times 198. And I get 4.01 times 10 to the minus 3 grams. Okay, I'm looking at the answer, and they give 0.0041 grams, which is the same, isn't it, basically? Same as me. All right, let me do the next one. Oops, pushed the wrong button. Okay, so this is the next one. Iodate ions react with sulfite ions in acidic solution of 5. As shown, the initial rate was found to be first order, and first order. Therefore, what's the rate? Well, the rate is equal to some sort of constant, rate constant, times the iodate concentration, times the sulfite concentration, times the hydrogen ion concentration. So there you go. So that's the rate. Now, with units of K, now this is the rate. So what's the units of K then? Well, K must equal this, moles, decimeters cubed per second, divided by concentration cubed, which is moles, decimeters to the minus 3, moles, decimeters to the minus 3, moles, decimeters to the minus 3. So that's going to cancel with just one of them. So recook this, and we get moles squared at the bottom, so that's to the minus 2. Decimeters to the minus 6, so it becomes plus 6 per second. So they're the units there. Hope that makes sense. Moles minus 2, decimeters 6 per second. Okay, I hope that makes sense. The rate depends on the pH of the solution. Assuming all other concentrations are the same, the rate of that is equal to the rate of this. Well, everything's going to, so we have to calculate X, don't we? The rate of that and over the rate of that. Everything's going to cancel apart from the pH 5 and the pH 6. Okay, so the pH at 5, everything's going to be the same. So what is the concentration at pH 5? Well, the concentration at pH 5 is going to be 10 to the minus 5. Okay, concentration at pH 4 is going to be 10 to the minus 4. So 10 to the minus 5 divided by 10 to the minus 4 is the same as 10 to the minus 5 times 10 to the 4, which is 10 to the minus 1. So the X is going to be 0.1. 0.10. Okay, I hope that makes sense, because everything else is going to cancel out. If you put this over another one of those, the only thing that's going to be different is that, so it's going to be 0.1. Okay, hope that makes sense. Let me go and dig the next one out. Okay, this is the last one for Les and Ollie for now. Calculate the volume of CO2 and cm cubed, form when 2.5 amps is delivered to the cell for 30 minutes or whatever. Assume the cell is operated at room conditions. Okay, so there's electrons there. So the first thing I want to do is find out the number of moles of electrons. So I'm going to find the charge pass first of all. Q equals IT. I is 2.5. T is 30 times 60 to get seconds, and calculate that. I think that's 4,500. So there's 4,500 coulombs. Now I want to get the number of moles of electrons, and we divide the number of coulombs divided by a Faraday, And that gives me the number of moles of electrons, so 96,500. And that gives me 0.0466 moles of electrons. I'm going to put that there. And therefore, to get the number of moles of CO2, I'm going to divide that number by 6. And I get 7.77. 7.77 times 10 to the minus 3. So the number of moles of CO2 is 7.77 times 10 to the minus 3. And now that's moles. And now I want cm cubed. So it's under room conditions. And room conditions, 1 mole is 24 decimeters cubed, or 24,000 centimeters cubed. So I'm going to times this number by the volume of CO2. I'm going to times it by 24,000 times 24,000 is equal to 186.5. 186.5. And the answer is 187. So presumably they want 3 sig fig there. All right, let me stop this now so I can post it. Okay, thanks very much. Bye-bye.